this computer. Good. So it's recording here. May 5th, 2025, week number 13, meeting number 20. And let me get something else too here that I'm gonna need. Let's see where we stopped first, right? Okay, so let's also get hold of the book. And see what we have done so far in the book. Launch. Refraction, reflection. We go wavefront and rays. We said that we worked on that. Reflection of light. Okay, we did those two. Okay, reflection angle of incidence is equal to the angle of reflection. And now we are going to do formation of image by a plane mirror. And I want to copy and paste the sections we are referring to. This is chapter 25. Okay, before, and by the way, I am still correcting report of lab 3, and I will finish it today. I'll finish it today. The sections that we are going to be covering, sections of chapter 25, we already covered this one. Okay, reflection of light. And now we are going to cover formation of image by a plane mirror. And then we are going to do spherical mirrors, formation of image by spherical mirrors, and the mirror equation, magnification equation. That's what we're going to do. Okay, remember what I told you about the principle of the least time. And that's something that's not in the book, right? Let's see if the book has it. Most likely the book doesn't have it. Let me search. Can we search it here? Least time. Nope, that doesn't have, nope, doesn't have list time. It has the list, it has time, but not list time. Yeah, not list time, okay? So keep that in mind. The principle of list time. It's just a law in physics, just another law in physics. It's not, so just recapping, right? Recapping. Although many books refer to the law of reflection, okay? This is not a law at all. This is not a law at all. It is just a consequence of something more genetic and powerful called the principle of least time. Principle of least time. And now we can start talking about the formation of images. And I'm going to need my drawings, my illustrations. Not this one, reflection and lens, reflection and mirror, right in here. Okay, so here you go. I made this, I made this illustration, right? Showing the plane of propagation of the waves. And it has an electric and magnetic field, one perpendicular to the other one. And the electric and magnetic field are oriented in such a way that whenever you cross E with B, you get the Poynting vector or the vector of propagation of the wave. This vector of propagation of the wave also coincides with the propagation of the light ray. Okay, here you go. Here's another representation of the front wave. Several front waves, one front wave here, another front wave here, another front wave here. And here go the Poynting vector propagating in the same direction of the light ray. Here is a point source that radiates in every possible direction. Here's another type of source. It's not a point source, but it's a light source. It emits light in a direction perpendicular, normal to the surface. And here is the case of a mirror, a planar mirror, right? So if you have a point source right in here, a light ray, let's go one by one. It's too much. Oh yeah, that's right. Yeah, if you have a point source right in here, a light ray going from S to another point P that you see right in here, and I'm going to do step by step here, right? Let's see if I can. Yeah. Okay, what's the path that the light ray takes from the point S to the point P, right? There are all sorts of possible path rays. And again, I'm going to do step by step here. That's just one possible path that the light ray can take, okay? Not that the light ray takes this specific path, but let's say, there's one possible path of the light ray. Another possible path of the light ray is this one right in here, okay? And there's, in reality, there are infinity number of path rays, right? And of the path for the path ray. And another possible path is this one that you see right in here. Among all those possible path rays, which one that nature actually chooses? Nature actually chooses the one that takes the least amount of time. for it to go from S to P. Light traveling at a speed of c, right, would take the least amount of time by going through a path in which the angle of reflection is equal to the angle of incidence. Okay? Okay, yeah, I cannot make it better, but ideally this point here should be right here in the middle, right? And but assume that I drew it perfectly. Okay, here you go. And that's gonna be the least amount of time this path is. And by the way, since the medium here is homogeneous, the least amount of time also coincides with the least distance traveled by the light ray, because the medium is homogeneous. And nope, not this one. Let's see. This one here. No, this one. Yeah, this one. And now I'm going to illustrate the angle of incidence and the angle of reflection. This here is the angle of incidence. Subscript. And this one right in here is the angle of reflection. One more student coming in. Oh, there are two here. Here you go. Reflection, and that's the angle of reflection. Let's make this font larger, right? And now here you go. Here's a light ray, right? That's incident at this point coming from the source. So I have the normal to the surface. I measure the angle of incidence of this light ray, and then I can expect that the angle of reflection is going to be equal to the angle of incidence. A little bit larger so you make it easier for you all to see. Okay. Another light ray coming from the source, incident at this angle of reflection, at this angle of incidence. The angle is going to be, reflection is going to be equal to the angle of incidence. That's another light ray, right? And so on. And then the next question is how we are going to how can we predict the image formation using this type of theory? Okay, it's rather simple, especially when it goes to planar arrays. And the same idea can be planar mirror, and the same idea can be used for spherical mirrors as well. All you need is only two different light rays. Okay, so let's just one light ray is not going to give you the position, the image formation. Okay, so in order to talk about image formation, comma, we need at least two different light rays. Just a single light ray wouldn't do the job. Just a single light ray, just a single light ray would not do the job, okay? And so let's see how we do that. Here you go. I'm gonna start with this one right here, with the first light ray, right? Okay, so what we do? Okay, so we extend this light ray behind the mirror, okay? That's what we do. Extend this light ray here behind the mirror. I have only one light ray so far, okay? Remember that I told you I'm gonna need two light rays, at least two light rays. But I'm gonna do something else to this light ray. I'm gonna dash it. Okay, and I'm gonna take away its arrow there at the tip. Format shape. Right, here you go. I took out, and now I have to shrink it a little bit and extend it. Okay, and by extend, I mean let me compress this one. Okay, so here you go. Extend it behind the mirror. That's my first light ray. Now I need my second light ray to find out where the image of this object is formed. The second light ray can be another one, let's say this one right in here, okay? So you go ahead, draw each light ray carefully, okay? Make sure that the angle of incidence is equal to the angle of reflection, and then you extend the light ray behind the mirror. And again, I'm going to dash it. Okay. And the point of intersection of those two light rays is the point where the image of the source is formed. In this case, the image of the source is formed behind the mirror. Makes sense, right? Because whenever we look at the mirror, it is as though that image is behind the mirror. Here you go. Here you go. So that I can call the image of the source prime. I'm going to put it here, S prime. S prime as it denotes the image of the source. And by the way, it ends up that this distance here of the image is equal to this distance right here. Okay? That's a very nice technique, works very well. And this type of technique works very well, not just for a planar mirror, but also for concave mirrors. Okay? So there is another way of drawing this type of image that you see right now. I'm gonna do the same for a different type of source. Here you go. We start with the mirror. We put an axis to this mirror. Okay, and then we put an object. Instead of a point source O, we put an object, we denote our object by an arrow. Now my object has a dimension. Okay, so here you go. That's the distance of the object to the mirror. We denote it by D naught. Let's take a look at the book. I want to make sure that we stay within the same notation. Same notation as the book is. Let's see. Object. Yeah, D naught. See that? The book uses the notation D naught as well. Okay, next. What do we do next? Okay, we start with a light ray that's parallel to the axis of the mirror. Because the angle of incidence is 0 degrees, this the angle of reflection is going to be 0 degrees as well. Okay, so the light ray is going to reflect on itself. And we do exactly what we did before. We get a second light ray. And now the second light ray is incident at the point where the axis of the mirror intercept the mirror itself. Here you go, here's the reflected light ray. Let's make sure that I got the right reflection, right? Sometimes we do not get everything in scale. Let's see if I got that in scale. Ideally, everything should be in scale. Okay, let's see. Yeah, it looks like I got it in scale. It looks like this angle here is going to be equal to this angle, right? And then what's next? We're going to extend the light ray that was reflected. Here you go. Here's the light ray that was reflected at the top, the light ray that was reflected at the bottom. Okay? And the point of intersection of those two light rays correspond to the point where I draw the image of my object. Okay, and you can do the same here for the other point here of the object, right? We don't have to do that, but if you do that also, you're gonna get the bottom of my image is going to be located, or the bottom of my image is going to be located along the bottom of my the bottom of the image of my object will be located at the axis of the mirror. Okay, that's the technique that we use in geometrical optics. And if you do the math, you end up finding out that the distance of the image coincides with the distance of the object. Why is that? Okay, because just similar triangles, right? You just do the similar triangles thing. This triangle that you see right in here is similar to this triangle here as well, which, by the way, is similar to this triangle, right? And which is similar to this triangle, right? And which is similar to this triangle. It's similar because this angle here is the same as this angle. this angle here is the same as this angle. So this triangle that you see here is similar to this triangle here. Because of that, this angle is the same as this one, and consequently, this distance here, di, distance of the image, must be equal to the distance of the other of the object, the distance of the object from the mirror. This is a very simple problem. There are more complicated problems you're going to find in your real life. Okay, so don't underestimate the simplicity of this theory. Okay, so for a planar mirror, comma, the distance of the image will be equal to the distance of the object to the mirror. The distance of the image to the mirror will be equal to the distance of the object to the mirror. What else do I have to do here? Technique, all right? Technique to find out the position of an image formed by a planar mirror. Okay, one. Draw the mirror. Two, draw the axis of the mirror. Three, draw an object, as an arrow, as a narrow. Place the bottom of the arrow at one of the points at the axis of the mirror. Okay, here you go. As an arrow. Place the bottom of the arrow at the axis of the mirror. And then draw a light ray parallel to the axis of the mirror from the top of the arrow. Okay? That's the incident. That is the incident light ray. Come on. Draw a light ray. Draw a reflected light ray. Draw the reflected light ray of item 4, right? The reflected light ray of item 4. The reflected light ray. This light ray must be reflected. This light ray must be reflected into the incident light ray. Okay, here you go. Draw the reflected light ray. Draw a second. Draw a light ray. Here you go. From the tip of the arrow, parallel to the axis of the mirror. Draw a second light ray from the tip of the arrow. Light ray. Draw a second light ray. Okay, second light ray from the tip of the arrow, making towards, here go, towards the point of intersection of the mirror, of the surface of the mirror, right? Of this surface of the mirror and the axis of the mirror. Okay. Draw the reflection of this second light ray. Okay. Use the law of reflection. And again, I'm going to put between quotes. Law of reflection. Use the law of reflection. Extend the two reflected light rays behind the mirror. Okay? The point of intersection of these two light rays, extend the two reflected light rays behind the mirror. The point of intersection of these two light rays behind the mirror is the point where the image of the top of the object is formed. Okay? Due to similarity of triangles, we find that the distance of the image from the mirror, the eye, is equal to the distance of the object to the mirror, d naught equal to di. Subscript. Like that, okay? And now I don't need any of that. It's a very simple technique. This is a very simple technique that can be extended for other types of mirrors, such as concave and convex mirrors. And now we are going to do the same for a concave mirror. So, and it's going to be a special type of concave mirror. Concave mirror is a mirror with a kind of a hole, right? It's possible to buy those mirrors in the pharmacies out there. Those mirrors can be used to magnify the image of an object. Okay, so here you go. Next we'll cover a spherical concave mirror. We will cover a spherical. Remember, it's a special type of concave mirror. It's a spherical mirror. Okay, spherical concave mirror. And then what you have to do? You have to visualize a sphere of radius r. In order to visualize this type of mirror, you have to visualize a sphere of radius r. Here you go, right in here. Here we have my sphere, right? What's next? You then cut a hubcap from this sphere. Okay, so here you go. That's a section of the sphere, right? We cut a section of the sphere, you're going to form a hubcap. What you end up having is a spherical concave mirror. This is a section of the sphere, right? I can illuminize, I can make this inner surface reflective. It's possible to do that. And we make this inner surface reflective. We form a concave mirror. The resulting device, the resulting mirror is something like that, okay? And I'm going to do even better than that. Here you go. I'm going to remove this one, right? Here's the center of the mirror. Here's the radius of curvature of the mirror. Okay? Can you picture that? Now, here you go. We do have a tangent. At this point here, we have a tangent here, right? We have a tangent to the surface of the mirror. And now any light ray passing through the center of curvature of the mirror is going to reflect back to it, because the angle of incidence is going to be 0 degrees and the angle of reflection is going to be 0 degrees. Okay? That's what I have here. The idea here is to predict the position of the image formed by this type of mirror, okay? The idea here is to find, is to predict, right? The position of an image, of the image of an object, in front this concave mirror. In order to predict that, in order to predict that, we need to know how different light rays are reflected by this concave mirror. Okay? Light rays passing through the center of curvature of the mirror. Curvature, here you go, curvature of the mirror. So I have proven to you, right? That light rays passing through the center of curvature of the mirror is going to reflect on itself, because its angle of incidence is going to be 0 degrees. Since any light ray that passes through the center of curvature is going to be perpendicular to a tangent plane, to a plane that's tangent to the spherical surface, it must reflect on itself, okay? Whether the light ray goes through here or if the light ray goes through here, okay? Or any other position of the mirror, it always will be reflected into itself. Okay? Because the light ray, the incident light ray, makes an angle of 0 degrees with the normal to the surface of the mirror. Okay, so here you go. Light rays pass through the center of curvature of the mirror. Every light ray that passes through the center of curvature of the mirror will be reflected on itself because its angle of incidence is because it makes a 0 degree angle with the normal with the direction that's normal, with the direction that's normal to the surface of the mirror. Okay. So we have our first puzzle here. Okay. We have our first puzzle solved here. So at least one light ray, we know how it behaves, right? And here you go. What else? Okay, that's how we represent a concave mirror. Instead of keep on drawing, going through the trouble of drawing a spherical surface like that, we simplify our drawing and we draw a concave mirror like that. Okay? This edges here tells you that the mirror is concave, even though the surface looks like planar, but we do something like that to simplify the drawing. Okay? And now, we're going to do exactly what we did with our planar mirror. We're going to draw an axis of the mirror that passes through the center of the mirror. Okay. We're going to mark the center of curvature of the mirror. Okay. And here you go. I'm going to draw here you go. A light ray parallel to the center to the axis of the mirror. Okay? So we know that light ray that passes through the center of curvature is going to be reflected on each other. And then what's going to happen if a light ray is parallel to the axis of the mirror, okay? A light ray that's parallel to the axis of the mirror is going to reflect towards a place between the center of curvature and the mirror. That's what you have to know, okay? And now this point that the mirror passes through has a special name. Okay, now there's an important approximation that I'm going to make here. If the diameter of the mirror is much smaller than the distance between the center of curvature and the center of the mirror, then this light ray that's parallel to the axis of the mirror will intersect the axis at half the distance between CC prime. Okay? Let us, every light. This you could help. The idea here is to predict in order to predict. Here you go. Light rays that passes through the center of curvature. Okay, that's the first light ray curvature. That's the first light ray that we're going to need to find out the position of the image. Now, what about light rays parallel to the axis of the mirror? Okay. These light rays are reflected towards a point in the axis of the mirror that is located half the distance of the center of curvature. Okay, that's my second light ray. And now that we have two light rays already, we can start building up the image of my mirror. Okay, light rays that are reflected, that are parallel to the axis of the mirror, are reflected toward the point in the axis of the mirror that's located half the distance of the center of curvature. This point is called the focal point. Okay, but don't forget, this is just an approximation. Strictly speaking, it doesn't work this way. Okay, strictly speaking, it doesn't, but it's a very good approximation. Okay, this is just an approximation that holds true whenever the diameter of the mirror, I'm going to denote it by D, is much smaller than the distance to the center of curvature. Center of curvature of the mirror, CC prime, okay? So if D is much less than CC prime, okay? And by CC prime, much less, I mean, less than 1/10 of C, okay? Then the focal point F, the focal point F will be located at a distance lowercase f, okay? That's going to be equal to CC prime divided by 2, okay? In other way, f where lowercase f is called the focal distance, not the focal point, but the focal distance. F is called the focal distance, okay? Capital F is a point. Lowercase f is a distance. Okay, so here we go. Let's see if I can illustrate that for you. Bye-bye. Yeah, here you go. Focal distance. Focal point, right? And I even going to draw another thing here. So we have 2 light rays. I'm going to show you some other light rays to help you out, okay? The distance that you see right in here. I'm going to move my focal point a little bit. Okay, so here you go. I don't need the arrows. I don't need this arrow. And I'm going to dash it, make it black color as well. Like that. This distance, the distance from F to the point C prime, okay, is called the focal distance. And now I'm gonna need this arrow here. And then I will label it with the letter lowercase f. That's the focal distance. Okay, equal to CC prime divided by 2. Like that, better, right? So 2 light rays. Let's see if we have one more light ray here. We can play with. Okay, so here you go. Light ray parallel to the axis is reflected towards the focal point. Another light ray parallel to the axis is reflected towards the focal point. Okay, that's located in the mirror, in the axis of the mirror. And then, just for the sake of having more than 2 light rays, we can also prove that any light ray that passes through the focal point is going to be reflected parallel to the axis of the mirror. It makes sense, right? It makes sense. It's just the opposite of the other. The other one, light rays parallel to the axis are reflected towards the focal point. But the inverse is also true. Okay? Any light ray that passes through the focal point is going to be reflected parallel to the axis of the mirror. Okay? Another light ray, a fourth light ray that we usually like to draw too, is this one right in here. The light ray that reflects exactly at the point that intersects the mirror with the axis of the mirror. Let's not forget that the angle of incidence is equal to the angle of reflection, right? At the very middle of the mirror, we can say that the surface is going to be almost planar, right? Infinitesimally planar. Why do I say that? I say that because a concave mirror is nothing but a bunch of planar surfaces that have different angles, okay? That's why. Do you believe that? Can you picture that in your mind? Several infinitesimal planar surfaces. That's what a concave mirror is all about. It's made of infinitesimal sections of a planar surface. Okay, if I have something like that here, let me go. I'm going to group this one. And then, let's see here. Okay, that's how you should picture a concave mirror. Make each of those sections smaller and smaller, and then you are going to have a smooth spherical surface. 4 different light rays for a planar mirror. Here you go. 2 different incident light rays, right? Incident at the center of the mirror. So one more light ray. Light rays parallel to the axis of the mirror. Light rays passing through the focal point F of the mirror. These light rays are reflected parallel to the axis of the mirror. And then we have this another light ray here. 4 different light rays incident at the center of the mirror. Light rays incident at the center of the mirror. They are reflected at the same angle of incidence. 4 different light rays. Okay? Summarizing, we have for more than enough to solve your problem. 1, light rays passing through the center of curvature C of the mirror. Light rays passing, light rays parallel to the axis of the mirror. 3, light rays passing through the focal point of the mirror. And finally, 4, in reality, you have infinite number of light rays, right? But you can use only those 4 to solve your problem. Light rays incident at the center of the mirror. 4 different light rays. We have 4 different light rays. 4 different light rays that you can use to solve your problem. Okay? Okay, and now what we're going to do here, we're going to predict the point where the image of an object is formed, okay? Given this mirror right here, with a given center of curvature, okay? We're going to do it in a qualitative fashion, in a geometrical fashion, by drawing the object, by drawing the whole problem, instead of calculating mathematically, okay? Now we can start solving the problem of predicting the position of the image of an object, okay? The position of the image of an object. 1, draw the concave mirror. 2, draw the axis of the mirror. 3, draw the center of curvature. Draw the position of the center of curvature of the mirror along its axis. Draw, what else? The position. C. Draw the point instead of the position. Draw the, yeah, that's okay. Draw the position of the focal point of the mirror along the mirror's along its axis. Its axis is the mirror, okay? The focal point F of the mirror along its axis. Let's take a look here. Here you go. The mirror, the axis of the mirror, the center of curvature of the mirror, the focal point of the mirror. And then what else do we have to draw? We have to draw the position of the object. Okay? Draw the position of the object somewhere along the axis of the mirror. Okay? Let's start with a position now, DO, e.g., DO greater than CC prime. Okay? Let's start with this example. And let's not forget we have C here, and we also have C prime here. Right? CC prime. That's the position of the object past the center of curvature. Okay, so let's take a little break now. Let me get my attendance sheet here. P07, P38 roster. Today is the 5th of May. Abir Ahmad, are you there?
Yes, I'm here.
Okay, thank you. Nestor Alvarado.
I'm here.
Thank you, Monte Ambarchian.
I'm here.
Thank you, Isabella Ballesteros.
Here.
Thank you, Isabella. Justus Bowden. I think I saw Justus here today, didn't I? Justus. Yeah, Justus is here, but doesn't look like he's in front of his computer. Alexandra.
I'm here, Professor.
Thank you. Benjamin Carvajal. Thank you. Elizabeth Castellano.
Here.
Thank you. Natalia Cordoba. Thank you. Jacqueline Delgadillo. Jacqueline is logged in, but looks like she's away from her computer. Jenny Diaz.
Here.
Okay, just came in. Okay, next is Valerie Diaz.
Here.
Next is Juan Escalera. Juan Escalera, I saw he logging in, but looks like it's not. Yeah, it's not here. I remember him logging in here. Okay, well, let's go for the next one. Bianca.
I'm here.
Thank you, Bianca. Edwin Gonzalez. Edwin, I don't see Edwin Gonzalez here. Next, Ellie Gonzalez.
Here, Professor.
Thank you, Ellie. Manuel Hernandez. Thank you, Manuel. Samantha Hubert. Thank you. CJ. Okay, actually. Okay. Let's see. Let's see here. Okay, so let me write that down. Biology major, right? Okay. Next is Amber Lopez. I don't see Amber Lopez here. Lots of students today. Arely Lopez. Thank you. Next is Genesis Lopez. I don't see Genesis here. Huh? Yeah. Mary. Are you here, Mary? I don't see Mary here. Galia? Galia or Galia, right? Let's see. Arely is here. Okay. Arely Lopez. Okay. Thank you. Ramon Olivares.
Here, Professor.
Next is Taylor Forn.
I'm here.
Next is Jeremy Pittman. I don't see Jeremy here. Next is Stephanie Ramos.
I'm here.
Thank you. Next is Leslie Rios.
I'm here.
Thank you. Jason Strait.
Here, Professor.
Thank you. And Hema. Are you there,
I'm
Hema?
here.
Okay,
Yes.
let's see how many students. Let's see if this number matches with my roster. 24. Yeah. Just one student that was away from the computer. Jacqueline Delgadillo, are you there? I don't hear from Jacqueline. Okay, so let's take our break now. Break from 10:50 a.m. to 11:05 a.m. Okay, so I see you soon.
Hello, Professor. I was here, but my mic and my keyboard wasn't working.
Who is that?
Jacqueline,
Jacqueline? Okay, let me fix that.
thank you.
Jacqueline, okay. Mary, are you there, Mary? Yes, okay, good. So now we have, good. So let's, so 4 different light rays. There are more light rays, of course. There's an infinite number of light rays, but those are the easiest one to visualize and the easiest one to draw. That's why, and don't forget, you need only 2, right? You need only 2 to form an image, to get the image formation. Now, here you go. So we managed to, my computer is misbehaving, folks. I do not know why. Let's see here. Yeah, okay. Okay, so let's start from the scratch, right? Since we stopped. Okay, first you draw the concave mirror. Then you draw the axis of the mirror. You draw its center of curvature. You draw its focal point. Locate its focal point. Then you locate this image. Let's do one more here. We still have the center of the mirror, right? Draw the center of the mirror. And then you draw the object. First, we start with the object past the focal point, the center of curvature. And then, here you go. I draw the light ray that's parallel to the axis. Okay, the light rays that are parallel to the axis are reflected towards the focal point, right? Focal point should be CC prime. Huh? Let's put the C prime right in here, right? And let me fix the remaining, okay, here. I want to put the C prime in every possible place here that I can. Okay, here you go. Okay, so, okay, light rays parallel to the axis is reflected towards the focal point. The focal point is located at CC prime divided by 2. CC prime divided by 2. Half the radius of curvature. Pick up. Okay. But don't forget, we need at least 2 light rays to locate the object, the formation of the image of the object. And you have 3 more light rays to choose from. Which one did I choose? I choose the one that passed through the focal point and is reflected parallel to the axis of the mirror. Okay? And now we have this point of intersection right in here. The point of the intersection is where the image of the tip of the arrow is formed. Here you go. Here's another one, the third light ray. You don't need a third light ray, but that's okay. And let's see if I get, okay, here you go. That's the point where If I do everything right, all the 3 light rays should be intersecting at exactly the same point. Okay? If I do everything right. And here I'm drawing just the 3 light rays. I didn't draw the 4th light ray, okay? And here, that's how I illustrated the image of the object. Let me, is this red arrow that you see right in here. And I'm going to make sure everybody can see this arrow properly. I'm going to bring it to the front now. It doesn't help, huh? Let's see if I can. Maybe I have to make it thicker. Yeah. Let's see if I can make it thicker. Strange. Bring to the front. Yeah, for some reason it's not going to the front. Strange. But no, there's nothing much I can do about that, right? Let's see if I'm gonna send that to the back. Ah, okay, now I got it. Okay. For some reason it didn't work, but now it did work. I for image, okay? Point I for image, capital I. That's the distance of the object to the mirror. The mirror is right in here. I'm gonna make it a little bit thicker than that so you can see more easily. What about now? Good, right? And that's the distance of the image to the mirror. You gotta practice that, okay? To get good at it. That's the case in which the object is past the center of curvature. Now let's see. Let's see if we have another problem here. Here you go, axis of. Now I'm going to put the object is past the center of curvature. Okay, let's move away from that. That's the other light ray, the green. Do you see the green light ray that I put it here? Now we have 4 light rays, right? The black, the green, the purple, and the red. They all should intersect at the same point. They all should intersect at the same point. And here's the image. The image is formed right in here. Okay, and that's H prime is the height of the image. H is the height of the object. H prime is the height of image. Obviously, this image is not amplified, right? This image is smaller than the size of the object. So this mirror is forming an image. And by the way, the image that is formed can be image. You can see this image with your naked eye. Okay, it's possible to see that. What we are doing here is not just some crazy theory that has no practical applications. Oh yeah, it does have practical applications. So much that we can, if you get an actual concave mirror, you can project an image of whatever you want in a screen. Okay, here you go. Let's see. Oh, I don't have more. What a shame. Looks like we'll have to do something. Okay. Let's do another one. But what I'm going to do, I'm going to move my object, okay? And I will do the following. I'm going to copy all of stuff here. One more. It's not okay, now I'm gonna move my object so you can see how this technique works for other positions of the object. Instead of past the center of curvature, I'm going to put this object exactly at the center of curvature. And then we're going to repeat the same thing. Okay? So here you go. I'm gonna get the light ray parallel to the axis, right? I don't need that anymore. Next, parallel to the axis. I don't need that, right? Yep. I'm going to show you the reflected light ray. Okay, I'm gonna copy this one here. And paste right in here. Yeah. Light ray that parallel to the axis reflects through the focal point. I don't need that anymore. Copy and paste. Next, you're going to need a second light ray. The second light ray that I got is this one that passes through the focal point and reflects parallel to the axis. Let's see if it fits. Let's see. Need that. This one right in here. Yeah, okay, now I need the second light ray. Getting a little bit lost here. Do I need that? Okay, I need this light ray now. Okay. The light ray that passes through the focal point. Don't forget, it has to go through the tip of the object, right? And pass through the focal point. Yeah. Like that. And now I don't need that anymore, right? But I'm going to need this light ray here, parallel to the axis. But wait a minute, first I have to copy this slide, duplicate this slide, right? And paste. Copy and paste. And we place the light ray that parallel to the axis right in here. Note, see that the image is formed very close to the point where the object is, okay? To be more precise, it's just supposed to be right in there, but most likely it didn't form. According to the theory, it should be, should be like right here. It looks like it didn't fit exactly before. Why is that? Because most likely because one of the points were not exactly at the proper position. Now let's invert this image. Like that. Right here. And then I'm going to change the color. This one. Let's see. Yeah, let's keep this way. Okay. And of course, we need that. We don't need that anymore. We can always get a third light ray. But first we need to copy this one. A third light ray would be the one that passes through the center of curvature. But since the object is sitting at the center of curvature, it's not gonna, oh yeah, it's gonna be possible, okay? So all you have to do is to get, to draw a line from the tip of the arrow through the focal point. Would be this vertical line, right? Would be this vertical line like that. And I'm gonna keep it, let's say, a green color, make it larger, thicker. Okay. And here you go. No, that's not this one I want. I want the other one. Yeah, that's the light ray from the tip of the arrow through the center of curvature. Okay. And it's intersecting right here. We can do a force light ray. The force light ray is going to be reflected exactly here. Okay. And I'm going to change its color. And it's going to be reflected through that point of intersection. Don't forget the angle of incidence, the angle of reflection is equal to the angle of incidence, right? The image should be formed like that. Okay, so another problem. Okay, break from, let's continue here, right? I didn't continue. Okay, draw the position of the object somewhere along the axis for D naught greater than CC prime. That's the first one that we did. Okay. Using at least two different light rays, we find that the position of the image of the object will be between the center of curvature and the center of the mirror, right? Let's take a look there. Going back to the first one. Yeah. Okay, between C and C prime. Okay. For an object, okay, I'm gonna put like that. Six. If you draw the position of the object at the center of curvature, we find that the image is located at the center of curvature as well. Curvature as well. Okay. We find the following. I'm gonna reorganize that using is between the center of curvature and the center of mirror. The position of the image of the object, okay, to the image of the object Object is inverted. Okay. If you draw the position of the object at the center of curvature, we find the following. We find the following. The image is located at the center of curvature as well. B, the image of the object is inverted. Okay? And then, you can have the other things too. You can repeat that for the object between the center of curvature and the focal point. And then the object between the focal point and the center of the mirror, okay? I'm not going to repeat that here because it's going to take too much time, but I'm going to give you a very good link that shows exactly, that allows you to simulate how those lenses behave. Let me see if I find it here for you. I cannot find it right now. So I'll have to do a search in the internet. And by the way, we're recording, right? Yeah, it looks like we're recording. Good. And simulation of a concave mirror. There are all sorts of websites out there. Where's the mirror? Let's see, this one, concave animation screen. Let's see here. Simulation, maybe it's this one. Maybe this one will help us. Okay, so here you go. Full screen, concave mirror. It's that. Yeah, I don't like this one. Okay, let's use it on this one. Doesn't look like it does what I wanted to do. Let's check this other one. Fat. Mirror. Let's see. Yeah, okay. Okay, here you go. See, and this one is what? I don't like the... We have 2 light rays here. We have 3 light rays. I don't like this one. I don't like this one. Marginal, principal, many. Let's see. No, I don't want that. Marginal. Yeah, I don't like this one. Principal. Okay, good. I like that. Okay. Parallel to the axis of the mirror is reflected towards the focal point. It doesn't show the center of curvature, right? Light rays at the center of the mirror is reflected at the same angle, and light rays through the focal point is reflected parallel. Unfortunately, they don't have the one that passed through the center of curvature. Let's see if we get another one. And look what happens as we move the object, right? As we move the object, this image, whenever the object is there at that point, at this point right in here, the position of the image coincides with the position of the object. So the center of curvature should be right in here at this point, okay? So here you go. Oh, and let me correct what I said here, okay? In my notes. I'm gonna make my notes better. The position of the image of the object is between the center of curvature and the focal point. And the focal point F. Focal point F is better now. Whenever the position of the object is greater than CC prime, the position of the image is going to be between the focal point and the center of curvature. That's what this simulation shows. Okay? As we approach the object, the image starts to be formed at further and further away, at a position that's further and further away from the mirror. See that? At this point, when the position of the object is at the center of curvature, the image is formed at the center of curvature as well. Okay? Now, as we keep approaching the object past this point, what happens to the image? The image is formed at a distance that's greater than the position of the object. Okay? Not only is formed at this position, but the size of the image ends up being greater than the size of the object. Okay? See what's happening here? Go as we get closer and closer. Look what happened to the image of the object. It grows larger and larger. It's just like the case of someone looking at the no, it's just like the case of someone getting an object in front of a concave mirror and projecting its image in a screen. Okay, this type of thing can be seen, can be verified in real life experimentally. And then what happens when the object reaches this point here? That's exactly the focal point. Look what happened. The image is not formed. Those light rays, those light rays that are being reflected, they become parallel to each other, and there is no formation of the image. Okay, the image we say that is improper. The image is improper. Okay, past the focal point, something else happens. We do get an image formation, but the image now is behind the mirror, not in front of the mirror. Okay? And this mirror here, and look what happened to the image. The image is now upright. Before, it's just not upright, right? It was inverted. Okay? When the image is formed to the left of the mirror, the image is inverted. When the image is formed to the right of the mirror, the image is upright. Okay? And that's the type of image that we see whenever we look very close at those concave mirrors. The image is amplified, is larger than the image of than the size of the object. Let's see if we can find another. Let's see, we have a nice simulation here that maybe this one is a good one. Yeah, okay. Let's see if we can work with this one, but it's not, okay, concave, nope. Concave mirror, okay. Okay, so here you go. Focal point, here's the center of curvature, see that? The object is a candle, right? And the image is being formed right in here where those two light rays are intersect. We can hardly see the image for some reason. Oh, yeah, here you go. Yeah, he drew very, very lightly. It's so difficult to see it. And he's not using the arrow with, okay. And here you go. At exactly the center of curvature, the position of the image coincides with the position of the object. And their sizes are the same. As we move past the center of curvature, the image grows larger and larger. The image is still in front of the mirror, right? At exactly the focal point, we have those two light rays parallel to each other and they do not intersect at all. That the image is improper. Okay, and then as we pass the focal point, the image now is formed behind the mirror, not in front of the mirror. This type of image is called virtual. The other one is called real image. Okay? So there are the following situations, right? Okay. We have the following situations for the concave mirror. 1. Object past the center of curvature. Object at the center of curvature. Object between the center of curvature C and the focal point F. Object at the focal point F. Object between the focal point and the center of the mirror, not the center of curvature, but the center of the mirror, right? So you have those 5 different situations. Object past the center of curvature, you know. Image is formed between C and F. Okay, between the center of curvature and the focal point. Image is inverted. Image is smaller than the object. Okay? Object at the center of curvature. Image is formed exactly at C. Image is inverted. Image has the same size of the object. Okay? And now I can copy that and paste right in here. I did those 2, right? That's what I did there in the PowerPoint. What I didn't do was the other 3, otherwise it would be too much work, right? But I did in the simulation. Okay, object between the center of curvature C and the focal point F. Image is formed past C, okay? Between C and infinite, right? And in a point at plus infinite. Positive is to the left. Image is still inverted. Image is larger than the object. Image is larger than the object. Okay. Image is formed at an infinitely distance. At an infinitely large distance. Image, we say that improper. Improper. Image is infinitely large. Is infinitely large. You can write like that. Okay. Is inverted. Now, object between focal point and the center of the mirror. Image is formed behind the mirror. Behind the mirror. Image is no longer inverted, but upright. Image is larger than the object, is larger than the object. Okay? So let's go here. Image is formed between C and F. Image is said to be real. Real image. Okay? Image is real. Image is real because it can be projected on to a screen, okay? Object at the center of curvature, we have the same thing. The image is still said to be real, okay? Object between center point P. Image is also real because it's in front of the mirror. At the focal point, image is improper. Okay. And here you go. Image is improper, and the image is in the process of becoming straight. Okay? It's in the process of becoming straight up. In the process of becoming upright. Let's put it this way, upright. In this case, image is said to be virtual image. Okay? So those are the different cases that you have to keep in mind. And I did all of that in the simulation. Let me get the link of the simulation. Although I prefer another simulation, this one here. I still don't like this one. Let's see if I can find another one. The one that I like. Concave mirror, let's see. Here you go. Yeah, I like this one better. Yeah, I like this one better. Okay. Okay, so let's play the movie. Full screen, right? Here you go. Let's play the movie. As I approach the mirror, the image is still inverted. As I get to the point of the center of curvature, the image is formed at the same point and has the same size of the object. Past this, and the image is still real, right? Past this point of center of curvature, the image becomes larger and is formed at a distance larger than that of the object. Okay? The closer we move towards the focal point, the larger the image becomes. At exactly the focal point, we have this improper image in which the image now is switching from an inverted image to an upright image. Okay? To an upright image. Upright image is formed behind the mirror. Inverted image is formed in front of the mirror. At this point here, the image is improper. And the image also is in the process of transitioning between a real image and a virtual image. Past the point of focal point, the image becomes virtual. Right here. Okay? And it's larger too. I cannot go any closer. The simulation doesn't let me get any closer, okay? And I will give you this link. I prefer this one here. I prefer this. There's another one that's even better than that. I cannot find it, but let's get check the simulation in the link, right? What time is that? 11:45. Oh man, we need a break, right? I'm starting to get burned out here. Break 11:45 a.m. to 12 noon. Okay? So I see you in 15 minutes. Okay. Okay, I'm back here. And let's share the screen. Okay. Okay, that's just the qualitative treatment. This is just the qualitative treatment. Qualitative treatment of geometrical optics. Okay, it's called geometrical optics because we use geometry to find out the position of the image of objects, right? That's why it's called geometrical optics. But now let's talk about the equations. From this, from this geometrical treatment, it is possible to find a set of equations. Okay, the first equation relates the position of the object, the positions of the object and image, relates the focal distance with the positions of the object and image. Okay, I'm not going to derive those equations here. I'm not going to derive these equations here, but their derivation is obtained again using a geometrical treatment. Okay, that's of similar triangles. Every book has something like has the derivation. Okay, so here you go. The first equation is this one right in here. They're not difficult to memorize. The inverse of the focal distance is equal to the inverse of the position of the object plus the inverse of the position of the image. Given the focal distance and the position of the object, we can find out the position of the image, right? Let's apply this equation for D naught equal to 2F. Okay. Find the position of the image for an object for D naught equal to 2F. As an example, you should already remember, we did this example with our drawings, right? So you should remember what's going to be the result. Solution. Here you go. D naught is equal to 2F, right? Let me put 2F right in here, 2F. Now we're going to solve this equation for DI. Like that. We have to isolate DI. We have to pass the term of 1 over 2F to the left and solve it. This one minus half of the same thing is going to be, 1 over 2F. And now we have this final result that you're already familiar with. The position of the image is going to be equal to the position of the object, right? That's the position of the object. For this specific case, we find the position of the image is also the same, equal to 2f. That's the first equation. Let's do another example. The example for the object sitting at position f, at the point f, right? You already know the final result, right? You're supposed to get a improper image. So here you go. Instead of 2f here, we put f, right? And then I'm gonna copy everything, paste it here, and just make some adjustments for what I did before. Here is f, right? We pass 1 over f to the other side. They're going to cancel out, right? So what we end up having here is 0. If 1 divided by di is equal to 0, it means that di must be a very large number. Must be, here you go. A very large number means going to infinity. This one right in here, right? That's the only one divided by a very large number is going to be very close to 0, right? So that's what is the case of the improper image. Okay. And now we can move on to the next result. There is another result that we get that you should know as well. The size of the object divided by the size of the image is equal to minus distance of the object divided by the distance of the image. Okay? And now let's repeat those two examples that we did for this equation now. Here we go. Example. Find the position, find the size of the image, right? Size of the image for d not equal to 2f, right? So let's use that here. We want find the size of image in terms of h naught, right? In terms of h naught. H dot for d not equal to 2f. We're going to use we need to use d naught and di, okay? Di for let's see here. Let me put yeah, d naught is equal to 2f, right? Yeah. Let's go to the next step. D naught becomes 2f. And we also know that di is going to be 2f as well. Okay? So here you go. What we get? We get minus 1. Okay? In the above, the negative number means that the image is inverted. Okay? And now we are going to do for the other case here. D naught equal to F. D naught equal to F. And we know that the I is a very large number from the previous example, right? Here you go. We know that the I goes to infinity. A finite number divided by a very large number is going to be equal to 0. And what does it mean? It means that H naught divided by HI, I'm going to do it, is equal to 0. Is equal to 0. For something that to hold, it means that HI, the height of the image, must be very large compared to the size of the image of the object. 4 different examples. And then we have one more equation. One more equation called the magnification. Magnification, Emma. Okay, the magnification Emma is given by the ratio of the distance of the image and the distance of the object. Either the distance of the image to the distance of the object or the height of the image and the height of the object. Okay? That's what we have for a concave mirror. That is, I found it another website. Let's see if this website is good. Oh yeah, I like this one better. Okay, I like this one better. Here you go, here's the object, right? Here you go, you can increase the size of the object and then you can position it anywhere, okay? And it even tells you if the image is virtual, inverted, upright, see here on the right side, and give you the actual numbers. Okay, that's the object. And let's see. Yeah, and here is the case for the convex mirror. That's the concave mirror, and that's the case of the convex mirror. They're smart, aren't they? Okay, they in a single simulation put both the concave mirror and the convex mirror. Okay. Go. All right. I like this one better. And I have it there in my notes. That was the one that I was trying to find. Another link for simulation of the mirror. Okay. Problems of mirror basically reduced to finding the position. Oh, I'm going to write that down here for you. Here you go. Position of the image, the magnification of the image, whether the image is inverted or not, and whether the image is real or virtual. Okay. Image. Let me give you some image for real images. For real images, the I is greater than 0. Okay. For virtual images, di is less than 0. Oops, less than 0. Okay. Image is inverted or not, okay? Inverted HI, inverted image, HI less than 0. Yeah, see? Less than 0, H. H naught is positive. H naught divided by HI is negative number. So if H naught is positive, it means the HI is negative. Okay. Upright image. Upright image, HI greater than 0. Okay. Position of the image. Okay. In front of the mirror. The eye. And by the way, in front of the concave mirror. Okay, let's put it this way for now. Behind the concave mirror. Concave mirror. The eye is less than 0. And I'm gonna, for concave mirror, okay? Mirrors. Let's be that specific. Now, for mirrors in general, if the image is on the same side, right, as the object, it is said to be real. It is said to be real. Another characteristic of a real image is that it can be projected onto a screen, not into, right? Onto a screen. Any projector, like the ones in the movie theater, project an image onto a screen, and consequently is a real image. And we can do the same. We can do the same with mirrors. If the image on the other side of the mirror, we say that the image is virtual. Okay. Okay, that's what we have for concave mirror. Now let's do convex mirror. What time is that? 12:20. We still have plenty of time. Half an hour. Let's go for convex mirrors now. Okay. This is the convex mirror. Okay, that's how we illustrate a convex mirror. Remember that a concave mirror had this edge upward like that, right? To the left, right? Convex mirror is on the other side. So here you go. So we can, just like before, we can come up with a axis for the mirror. But now the center of curvature of the mirror is going to be to the right, not to the left. Because the concave surface, right? It's just like having a spherical surface here, right? And then we have this, the center of curvature on the other side that I call C prime. We're going to need that. And then we have the focal point F prime on the other side of the mirror. And the other focal point on the right side of the mirror. We can go ahead and put an object past the C prime. And by the way, the results that we get for the convex mirror are much simpler than the results that we get for the concave mirror, okay? The problem of the convex mirror is easier to solve than a problem for the concave mirror. We use concave mirrors in the side mirrors of our car, right? We see a very small image, but why the image is small? The image is small because it's taking that mirror is capable of imaging things larger, right? A larger angle. You can see a larger angle than with a regular flat mirror. And here you go. So that's the distance of the object. Let's see how we can get an image formed by this mirror. Here you go. Light parallel to the axis, right, is going to be reflected, diverged, right, away. The image is not going to be focused, but its extension is going to pass through the focal point of the other side. And here I want to put F prime so we can discern one from the other. Okay? And then we have this other light ray, which, by the way, is passing through the focal point. Since this light ray is passing through the focal point, it's going to be reflected parallel to the axis of the mirror. So the procedure is exactly the same as we had for the concave mirror. And now we have the intersection of those two reflected light rays, right? And we can start drawing the image. But before doing that, let's show a third light ray that passes through the center of curvature. Light ray that passes through the center of curvature is reflected into itself, okay? And the third intersection must be the same point as the intersection of the other two light rays. And here, right in here, is the image that's formed. It's smaller than the object itself. Let's see, can we do that? Here you go, that's the distance of the image. And the equations are exactly the same. The only difference now is that the focal point and the center of curvature of this mirror is going to be negative, okay? And now we can play with the convex mirror. So here you go. as far as away as we can. Okay, look where the image is formed. As I approach the mirror, the image grows in size. Okay, and it's always upright. At the point where the object is exactly at the position of the mirror, the size of the image coincides with the size of the object. Okay? Do you see? It's much simpler. This is a much simpler problem because it has only one result. The image is always virtual, upright, and smaller. Okay? We can write it down here for a convex mirror, comma, the focal distance is less than 0, and the center of curvature is also less than 0. Okay. The result is an image that is always upright, virtual, and smaller. The same equation applies. Okay, the same equation applies for convex mirror. The focal distance is less than 0. So we can here write like that, you know? So we got negative number here, and then what else? We turn this F as being the magnitude. Here you go, magnitude of F. So if we want to solve for the position of the image, we have to pass the D naught to the other side. And note that the I will always be less than 0. According to this equation, the I will always be less than 0. But that assuming, okay, assuming, of course, that D naught is greater than 0. There are situations in which D naught can be less than 0, right? Okay. Let's put it this way, for D naught greater than 0, for D naught greater than 0, 1 over di is going to be less than 0. Di is going to be less than 0. There are situations in which D naught is less than 0, okay? But we are not going to cover that. But we are not going to cover in which D naught is less than 0. But we will not cover that here in this course. In this case, image is always virtual. I can even come up with an equation for the position of the image. I'm going to reinvert. I'm going to invert, right? Invert this equation. so I can have a more straightforward equation. Okay, so what we end up having for the I is something like that. So if D naught is positive, okay, this term will always be positive, but with the negative sign in front of it. This term will always be negative for D naught positive. What about the magnification? Magnification is di over d naught. Okay. Di is given by this equation. I put it right in here. Don't forget it's the magnitude. D naught, okay, is downstairs. You don't need to do any more than that. This D naught cancel out with this D naught. We get what is left because this whole thing is inside a magnitude sign, right? The negative sign can be dropped out. And we get this ratio, which, by the way, will always be less than 1 for D naught positive. Okay? So you always get an image that is smaller than the object. And we have that other case, H naught over HI. Here you go. Let's get that. Here you go. That's the one. H naught over HI. Okay. I calculate the DI here. I am replacing the DI right here. This negative sign is going to cancel this negative sign. So I'm going to erase it. The D naught is going to cancel the other D naught downstairs. And we can invert the denominator. D naught plus F. Oh. And you can see that for positive D naught, right? This ratio is always greater than 1. What does it mean? It means that the size of the object will always be greater than the size of the image. Right? Those are the conditions that we have. And let's take a look at the chapter. What we have covered. We found the equation magnification. Looks like we covered everything. Let's see here. Sections chapter 25. 1236, wavefronts and rays, reflection of light, formation of image by a planar mirror, spherical mirrors, formation of image by spherical mirrors, the mirror equation, the magnification equation. We covered everything. Let's take a look at the book. Okay, that's the planar mirror. That's the spherical mirror. Here you go. Here's the hubcap, right? If it is this surface here that is reflective, aluminized, right? That would be a convex mirror. But if the other surface is reflective surface, then it will be a concave mirror. The convex mirror is usually called the negative mirror as well, and this one a positive mirror. Here you go, here the triangles that I mentioned to you. Okay, we use those triangles to obtain that equation for the equation for the mirror that you saw. When I told you that the focal point is half the distance of the curvature, this is just in reality, this is just an approximation. This is just an approximation for the case in which the diameter of the mirror is much smaller than the curvature of the mirror, right? If you get a curvature of the mirror, if you get a diameter of the mirror that is very close to the diameter of the mirror, then we do not have a focal point. We have this type of behavior here, right? Not all light is reflected through the focal point. Okay, let's write that down. Okay. Remember that F equal to CC prime divided by 2 is only an approximation for the case in which the diameter of the mirror is much less than CC prime. Okay? If something like that doesn't happen, if something like that does not hold, then the light rays do not converge exactly to a single focal point F. Okay, and that what we end up having is something like that. The image is not focused. Okay, the image is not focused. So what does it mean? What does it mean? It means that a spherical mirror is not the ideal device for focusing the image. Okay? This means that the spherical mirror is not the ideal mirror for focusing the light. The ideal mirror is what we call a parabolic mirror. Not a spherical mirror, but a parabolic surface. A mirror with a parabolics. But the ideal mirror is the one with a parabolic surface. That's the ideal mirror, but it's much more difficult to do it. Much more difficult to craft, okay? Although this is the ideal mirror, it is much more difficult to craft than the spherical one. On the light, okay? Can you remember that? Okay, that's what that illustration is all about. That's what this illustration is all about. Does he talk about parabolic mirror? Doesn't look like he talked about parabolic. Oh yeah, he does talk about parabolic mirrors. Okay, so it's a type of solar panel, right? They have this, I do not know if you know about that. It's a very interesting facility that we have in the Mojave Desert for generating electricity using a different setup. Okay, you have rows and rows of those parabolic mirrors focusing light exactly at this point. Remember, they do not use a spherical surface. They use a parabolic surface. Just like the shape of this curvature that you see here is that of a parabola. Okay, it focuses better. This surface focuses better the light from the sun. And what we have here, we have a pipe, okay, running through all those mirrors. This pipe is located at the focus of these mirrors, of those mirrors, at the focal point of those mirrors. And we have this pipe here is filled with oil, okay, with oil. Many such rows are used for solar thermal electric plant in the Mojave Desert. It's a different way of generating electricity. Okay, what time is that? 12:43. Okay, here goes sodium unit and engine. That's it. Let's take a look at this one. Now we can skip this one. Shows instrumental device, national sun DLC. Check a section on the surface of a hollow sphere has a radius of curvature 0.6 meter, and both the inside and outside surface has a mirror-like polish. Okay, what are the focal lengths of the inside and outside surfaces? Okay. Hollow sphere is a spherical mirror. Okay. If the curvature is 0.6, right, it means that the focal length or focal distance is 0.3 meters. Formation of mirror of image by spherical mirror. Okay, I did all of that. See here the object between the focal point and the center of curvature. We have three different light rays here. One parallel to the axis passing through the focal point, another one passing through the focal point and being reflected parallel to the axis, and another light ray passing through the center of curvature. Okay? You go. The magnified image of someone looking very close to a concave mirror. Those mirrors are very cheap nowadays. We can buy one of those there at the drugstore. They are manufacturing mass. During my time, we didn't have those things, those nice tools, you know, those nice toys. And then we have the case of a head-up display that we're not gonna ray tracing. Okay, that's we call this technique that I taught to you, the ray tracing technique. And here you go, the formation of an image due to a convex mirror. Do you see the angle that you can see? The image formed by a convex mirror is much wider. And this skier is a skier that's here. You know, he has a helmet that's chromed, and because the helmet has this spherical surface, this spherical outside the spherical surface of the helmet acts like a convex mirror, producing the image of the spectators that are here behind. The mirror equation. Okay, so here goes, here the triangle, right? And 12:47, 3 more minutes to go. I think we can stop here, okay? Here's the James Webb Space Telescope made of several smaller mirrors. And Yeah, we're done with this chapter. So if you don't have any questions, I'm gonna have my office hours right now. If you stay around, let me know. And otherwise, I see you on Wednesday. Okay?
Hey, Professor.
Thank you. Bye bye. Yeah. Let me stop recording here. Stop share and stop recording, right?